right, this is our video for collisions in energy. So this is for if you were absent or if you just want another look at those energy collisions class problems. All right, before we get to the problems, this is just other things for you to know, other things for your notes for you to make sure that you are aware of before we start these collisions. All right, where have we seen this word collisions before in this year? You might remember all the way back to our conservation of momentum, right? Whenever something collides, we need to conserve the total momentum that this thing has. All right, so let's say we have two objects that are aimed at each other. Let's call object 1, object 2, some initial velocity 1, some initial velocity 2, v1 naught, v2 naught. Then they collide, right? Bang, boom. Okay, and then we get object 1 bounces back, object 2 bounces back that way. Okay. Right, so what's the initial momentum that this system has? Well, it's m1 v1 naught plus m2 v2 naught, right? Everything that's moving, and then everything that's moving finally. So m1 v1 final plus m2 v2 final. Okay. All right, and this is v1 final, and this is v2 final. There you go. All right, so that's a collision. That's what we've done with conservation of momentum. All right, the important things to remember on this, though, and let's get a good color here. Important things to remember, right? This one's moving to the right, v1 naught. So we will call that, right? We'll probably call that positive to the right. So what does this mean to the left then? Well, that means v2 naught is going to be negative. But what does that also mean about v1 final? Well, the same thing. If it's moving to the left, it'll be negative. So we've got v2 naught and v1 final. Both of those are probably negative. Negative. Okay, that's just an important thing to remember when you're plugging these velocities in, because momentum is a vector. We have to pay attention to what direction it's going. Okay. So that's collisions in energy, or collisions in momentum up to that point. Right, we had mentioned two words for types of collisions. We talked about inelastic collisions and we talked about elastic collisions. Okay, but what was special about all these things? Well, we'd said inelastic means they stick together and elastic means they bounce apart. This is only a partial truth. That's only a partial truth, so don't trust that. Because what the real truth is that elastic collisions, now that we're looking at this through the lens of energy, elastic collisions, all kinetic energy that the objects of the system have initially is equal to the kinetic energy that it has finally. Right, we know this relationship, E initial equals E final, and it has to unless there's some amount of work that's done. But let's say for the sake of this problem that there's just no outside forces. So it's just energy initial equals energy final. We know that must be true. However, an elastic collision is special because it has all of the kinetic energy is conserved as kinetic energy. All right, if I were to take a tennis ball, it's a very tennis ball-like color. If I were to take a little tennis ball here, and throw the tennis ball, try to throw the tennis ball at the ground, right? Throw the tennis ball at the ground. What happens? All right, well, we hear some sort of noise from that collision. We hear a noise. So some of that energy that the ball had initially is dissipated as sound energy. So we start with some kinetic energy, and then, right, we get some sound energy, right? Some energy is sound, and then it moves back up, so there's some kinetic energy back up. But then there's a little bit of thermal energy, right? The tennis ball heats up a bit, which is kind of interesting. But kinetic energy turns into all these different things, right? There's kinetic energy, there's sound energy, there's thermal energy. But what if we were to bounce a ball with no sound energy? What if we were to bounce a ball, no loss to thermal energy? Oh, another thing, we had air resistance, right? The ever constant plague of physics. Air resistance. What if we just said, no, air resistance doesn't exist? What if we were able to say that the kinetic energy down is equal to just the kinetic energy up? Right, that tennis ball would bounce down, it would hit this point, and then it would bounce right back up to the exact same height that it was at before. And then it would go back down because of gravity, bounce on the floor, and go back up to the exact same height it was before. That would be a perfectly elastic collision. Now, we don't have any of these truly in real life because, right, of all these things, we've got the sound energy, we've got the thermal energy, we've got the air resistance, and all those. But we can theorize about these elastic collisions using this kinetic energy initial equals kinetic energy final. We can theorize about all these problems. Okay, so we know this. We know this momentum problem. I'm going to get us to look at this a little further down. We know this momentum. Let's duplicate that, slide it on down. Okay. So momentum, right? If we look at momentum, that must be conserved every single time, period, end of story, the end, goodbye, no questions. However, if we want to take a perfectly elastic collision, that means, right, what we were just looking at, a perfectly elastic collision, that means that our initial kinetic energy has to equal our final kinetic energy. So if we take a look at this same system with the two balls bouncing in, colliding, and then the two balls going on their own separate ways. Right? If we look at that, then we get this relationship, right? 1/2 m1 v1 naught squared plus 1/2 m2 v2 naught squared equals 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. All right, kinetic energy of object 1 initial, kinetic energy of object 1 final, kinetic energy of object 2 initial, kinetic energy of object 2 final, because energy is just a scalar quantity. And it's that scalar quantity because, right, we could still look at V2 initial and V1 final as being negatives, but since we square this V2 initial and since we square this V1 final, it doesn't matter if it's positive or negative. It really doesn't matter at all. Okay. All right, so if we were to take this relationship, we can multiply the entire thing by 2. So that's going to help us get rid of some of those pesky little 1/2s that just make math a little bit harder. So if we multiply this whole equation by 2, we get all of this relationship. M1 V1 naught squared plus M2 V2 naught squared. That turns into M1 V1 final squared plus M2 V2 final squared. These look basically identical, except for the fact that we have all these squareds on this energy equation. Otherwise, these two equations look identical. But what this means, if we were to take these two equations and combine them together, you get something that's kind of cool. If you want to be convinced of the math of this at some point or shown how we get this, please come and see me. I'm more than happy to help. But if you take this equation and you combine them together for a perfectly elastic collision, you get this relationship. V1 initial plus V1 final equals V2 initial plus V2 final. It's awesome. Usually in physics, you can tell you've done something right when it simplifies down to just a stupid, easy expression. Now remember, right? This one's going to be negative. This one's going to be negative. V1 final and V2 initial are going to be negatives, but we get that. We get that relationship out of this. So if I ever ask you the question, check if this is a perfectly elastic collision, this is a great place for you to start. Or this is a great equation for you to use. Let me rephrase that. You'll start somewhere else, but that's a great equation for you to use. All right. With the context of that, let's take a look at some of these practice problems. So if I can get over to my browser, here we go. I'm on class problems. This is page 17 in your workbook. By the way, these are all groundhog themed because the year I wrote these, I taught this on Groundhog Day. And then I decided to just keep it because groundhogs are really cute to imagine running at each other and just bouncing off. Okay. So we've got question number one. One groundhog. One groundhog has a mass of 4.52 kilograms. Right, groundhog. My groundhogs look a lot like potatoes with ears because I'm a terrible artist. Groundhog 1, mass of 4.52 kilograms, and runs with a velocity or with a speed of 3.60 meters per second. Runs into another groundhog who just stands still. Another groundhog who's just standing still, minding his own business. After this collision, okay, boom. The first groundhog is stopped in his tracks. This one looks a little bit more potato-ish than the other. The first groundhog is just stopped in his tracks. And then the second groundhog goes flying. Second groundhog flies off at 2.86 meters per second. All right, here's our question. Is this collision perfectly elastic? Question mark. Justify your answer. All right. Well, because this is a collision, we need to check some stuff. Anytime we have a collision, this is the first thing you check. P naught equals P final. If this is true, then we can check if it's an elastic collision. But first, we need to check just, does this collision follow the laws of physics? So, right, what do we have moving initially? Well, we just have this groundhog. Groundhog number 1. I'll give them nice chest tattoos with numbers 1 and 2. We just have groundhog 1 moving, so M1, V1 initial, because groundhog 2, he's not moving. He's just at rest. And then finally, well, groundhog 1's just at rest, so all we have is groundhog 2, M2, V2 final. All right, so that's how we check our conservation of momentum. Let's plug some things in. 4.52 kilograms. He's off at 3.60 meters per second. Mass of 2. And by the way, this is an equals question mark because we don't know if they're equal yet. We're checking to see. So that's how I'll notate that, is equal sign with a question mark over it. Mass 2 is 5.3 kilograms, flies off at 2.86 meters per second. Okay. I'll get my calculator pulled up here. I have to open the right program. Here we go. Finish. There it is. So get the calculator here. All right, we got 4.52 times 3.6. That gives me 16.3 over here. 16.3. Oh, and remember, this is a momentum. What units does momentum have? Kilogram meter per second, right? Mass times velocity. So that's what I have on the left, and I need to see, is this equal to, question mark equals, 5.3 times 2.86. 15.2 kilogram meters per second. Is that true? Is this true? No, it is not. So we might say, no. This is not a perfectly elastic collision because, right, P naught is not equal to P final. Momentum is not conserved. Okay. That's really all this is. That's really all there is to one of these. However, sometimes you will get the answer yes to momentum being conserved. Sometimes you'll get that answer yes. But that doesn't make it perfectly elastic. Right? For something to be perfectly elastic, what has to be true? What has to be true for perfectly elastic collision? Kinetic energy initial equals kinetic energy final. Okay, so now we can test this. Well, kinetic energy initial, right? That's just going to be 1/2 m1 v1 naught squared, okay? Because the other guy is not moving. And then finally, now the first groundhog's not moving, so we're just going to do the second groundhog, m2 v2 final squared. All right, 1/2s go away. So we could either check m1 v1 naught squared equals m2 v2 final squared. Or, right, you know how to do that. I can let you do this. By the way, again, this is our question mark equals. We don't know if they're equal. Or the equation that I just showed you on the previous page. v1 naught plus v1 final equals v2 naught plus v2 final. The nifty thing about this equation is it includes both conservation of momentum and conservation of kinetic energy as kinetic energy. So this tests both. Is momentum conserved and is it an elastic collision? So actually, we could have just started here. We could have just started here and said, okay, V1 initial, 3.6 plus V1 final, 0, equals V2 initial, 0, plus V2 final, 2.86. Well, is this true? Does 3.6 equal 2.86? No, it does not. You'd say no, because, so this is not a perfectly elastic collision because not all kinetic energy is conserved as kinetic energy. And we can notate that as KE initial is not equal to KE final. Okay, so there's the two separate methods of solving this question. All right. We are now going to move on. Number 2 here. Number 2 is not the hardest of questions. Number 2, not the hardest of questions, but it's a good one to understand. On this question number 2, it's just fill in the blanks. Right? For a perfectly elastic collision, what must be true? Well, it's defined as when kinetic energy is conserved as kinetic energy. Kinetic energy. That's just the definition of an elastic collision. To check this, right, the first thing we have to do for any collision, first thing we have to do is use the conservation of momentum. And I just shorthanded as COM. Conservation of momentum. But then the second thing we have to check, right, we have to use the conservation of energy. Conservation of energy. And this one more specifically is going to be of kinetic energy because of just the definition of an elastic collision. So then you would set up KE initial equals KE final. KE final, that's what we have to check. All right. So that's just our fill in the blanks. This is the fundamental understanding of a perfectly elastic collision. All right. With that, let's go to question 3. Question 3 asks us, all right, got a couple other groundhogs. These are very light little groundhogs. Got to be the babies of the litter. Yeah, being 0.4 kilograms, this groundhog can't be more than a couple days old. All right, 2 groundhogs collide straight on with each other. So I'll draw more of my potatoes with ears. That's the best I can do for groundhog. 2 groundhogs collide straight on with each other. They look a little worried, they're running straight at each other. Okay. Groundhog A has a mass of 0.4 kilograms and initial velocity 1.2 meters per second. Groundhog B has a mass of 0.6 kilograms and an initial velocity of 1.4 meters per second. What's the final velocity of each groundhog? Of each groundhog. Okay. Well, this is a collision. What's the best place to start in collisions? No matter what? Momentum initial equals momentum final. Okay. So we'll get mass of groundhog A, V naught of groundhog A, plus mass of B, V naught of B. That has to equal our final momentum. So mass of A, V final A, plus mass of B, V final B. But what else do we know about this collision? We know it is perfectly elastic. So that means that our kinetic energy initial has to equal our kinetic energy final. Has to. Which means V naught A plus V final A has to equal V naught B plus V final B. Right? That's our shortcut equation. You could throw in all of this 1/2 MAV A naught squared plus 1/2 MB VB naught squared. You could do all that and then equals the finals of all those. But that's just a lot of extra work to go through a lot of extra squareds, especially. That makes the math a lot harder. And I'm not so interested in doing that. If there's an easier way, let's do so. All right, so we're looking for velocity final A and velocity final B. We need the final velocity of both of them. Well, here, take a look at this. 2 equations, 2 unknowns. Right, we could plug these in, do 2 equations, 2 unknowns, systems of equations. You could work that out by hand. It's probably good practice for you to try to work that out by hand at some point. However, if you were to look at my course schedule, right, I have on this energy unit for today, we've got elastic collisions spreadsheet calculator. If you pop open this elastic collision spreadsheet calculator. This shows you, I spent a lot of time programming this during a snow day. Spent a lot of extra snow day time doing this instead of, making snow angels. So this elastic collisions calculator is really, really helpful because it does the system of equations for you. It does the system of equations for you. Now, when I programmed this spreadsheet, I used the harder version of the kinetic energy equation. I used all the V squareds that you get with kinetic energy. What that does when you use all those V squareds is you get a quadratic expression when you solve this all. So there becomes a plus and minus. That's what these columns are. So we've got option 1 of V1 final and option 2 of V1 final. And then option 1 of V2 final, option 2 V2 final. So this right side is for the final velocity of object 2. This left side is the final velocity of object 1. Now the green columns go together. Those are a pair. Those would be from the quadratic expression. That was from the much harder version of the equation. I mean, you can see the equation up here. You can see that equation. That took me forever. But from the harder version of that equation, right, green columns were plus in the quadratic formula, and then the yellow columns were minus in the quadratic formula, because we have the plus or minus the square root of all this stuff. So the green columns go together. That's why they're both labeled option 1 and option 1. The yellow columns go together. That's why they're labeled option 2 and option 2. What you have to do is decide which one to use based on the positive versus negative signs. The positive versus negative signs. All right, because in our groundhogs here, we have groundhog A. All right, groundhog A is moving in the positive direction. Groundhog B is moving in the negative direction. So when we have groundhog A in this positive direction and groundhog B in the negative direction, right, positive to the right, negative to the left, how are they going to bounce off each other? Well, groundhog B is going to come back and bounce that way. So that'd be groundhog B. And groundhog A will come back and bounce to this direction. So right, we have this will be a negative and this will be a negative. So we need velocity of A final to be a negative number. Okay, so let's plug this all in. So I have mass of groundhog 1, 0.4 kilograms, and he's moving at 1.2 meters per second. It automatically will populate with your kinetic energy initial and your momentum initial. Now if we get our mass 2, so mass B, 0.6 kilograms, 0.6 kilograms, and he was moving to the left at 1.4 meters per second. That means we have to plug in negative 1.4 meters per second. All right, now you see all these numbers auto-populate. We've got kinetic energy of object 2, momentum of object 2, or I should say of groundhog B. And you get all these different, not all these different, these two different systems here. All right, this shows you kinetic energy is conserved because this total between those two will equal that total between those two. Same with momentum, right? Momentum has to be conserved. So if you add those two numbers, you get the same as if you added those two numbers. All right, but we're concerned with which one do we need to use? Do we need to use the green columns, the option 1, or do we need to use these yellow columns, the option 2? Well, if we had groundhog A moving forward, initially groundhog A has to move backward now. That means we need we need object A or object 1 to have a negative final velocity. So to me, that looks like those numbers. Where groundhog A will bounce back to the left, groundhog B will bounce back to the right. Okay, so this means groundhog A's final velocity is 1.92 meters per second to the left. So V final of A equals 1.92 meters per second to the left. And then velocity final of groundhog B, well, what did it say? 0.68 equals 0.68 meters per second. That was positive number, so it means to the right. There you go. There's your answer. So this spreadsheet saves you a lot of time. Spreadsheet will save you a lot of time. So on that course schedule, all right, just go ahead, click on that link, and I tell you right here, make a copy for yourself, make a copy for your homework so you can get file, make a copy, boom. There you go. All right, so that was question number 3. Your homework will have, I think it's 2 questions where I don't give you any of the final velocities and I ask you for both of the final velocities. Just use the spreadsheet whenever you have to do that. All right. We've got one more question here broken down into 3 parts. So, question number 4. We've got, I like this question because it shows you just how stupid scary semi-trucks can be. Okay. We've got a semi-truck. All right, there's the truck. Or I guess this is the truck and that was the trailer. Boom. All right, 18-wheelers have, I think, that many wheels. Something like that. Okay, there's our semi-truck. 15,000 kilograms. 15,000 kilograms. Just as a FYI, that's about 33,000 pounds. It's about 33,000 pounds, which is just monstrous. Driven by a groundhog. Okay. Right, I had to get the groundhogs in there somewhere. Driven by a groundhog. Moving at 53 miles per hour, so that's 23.3 meters per second. I already did those unit conversions for you. Let's say they run head on into a small sedan. I say no groundhogs because that would not go well. Run head on into a little small sedan that's moving in the opposite direction, mass of 1650 kilograms, and it's moving at 25.5 meters per second, or 58 miles per hour. Right, so these are fairly standard highway speeds. Right, maybe a 55 mile an hour speed limit on the highway. That's pretty typical. Okay. If they were to bounce off perfectly elastically, what would be the sedan's final velocity? So we're looking v final of sedan equals question mark. Well, do we know either of the final velocities? No, we don't. We don't know v final of the truck either. That's also a question mark. We don't need to know it, but we don't know it. So if we don't know either of them, where do you go? Well, let's go to the spreadsheet. All right, so let's go to the spreadsheet here. Well, on this, right, okay, I give you the truck 15,000 kilograms moving at 23.3 miles per hour, meters per second, 23.3 meters per second. You might notice this kinetic energy initial, 4 million joules of kinetic energy. 4 million joules of kinetic energy. So then if we put in the sedan, right, 1650 kilograms, but 25.5 meters per second, the opposite direction, which means negative 25.5. Okay, this one's just about 500,000 joules. Just about 500,000 joules. Okay. So if we look over at our options, we've got either 13.63 or 62.43. And 62.43. That's one pair. The other pair would be 23.3 and negative 25.5. Oh, you know what's strange about this? This option 2 column, both of these yellows, option 2, those are exactly the same numbers as what we started with, this option 1. This initial velocities. Well, that's not going to work, right? There's a collision, so do the velocities change? Yeah, the velocities are going to change. What that means is that this option 1, this green column, is going to be our numbers. Okay, but what this means, our truck was moving at 23.3 meters per second. Now he's moving at 16.63 or 13.63 meters per second. The sedan was moving at negative 25.5, and now it is moving at positive 62.43. Positive 62.43. So 13.63 and 62.43. So velocity final of the truck, 13.63 meters per second. Velocity final of the sedan, what did we say it was? 62.43 meters per second. And that's that way. Right? They're both this way. They're both positive numbers, so they're both to the right because this 25.5 was negative. So this means, okay, the truck slowed down. The truck went to a little over half of its velocity. But then this sedan, whoever was in there, whoever little stick figure was driving that sedan, they just went from 25.5 meters per second in one direction, so 58 miles per hour in one direction, to 62.43 meters per second, and that's roughly equivalent to about 140 miles per hour. So they just went from 58 one direction to 140 the other direction. Yikes. Okay. But we know that's not real. That's not a real number, right? Because you get perfectly elastic collisions. That's how you get that number. Collisions aren't perfectly elastic. That would mean that we'd have to have no sound energy. So in this crash, whatever that crash looks like, it would have to not make a single sound. The cars would have to not be impacted, anything like that. We know that's not true. So let's take a look at some slightly more real facets of this problem. All right, part B, if the collision took place over the 1.4 meter long crumple zone, what was the force that the semi-truck exerted on the sedan? Okay, we're going to still use the perfectly elastic collision number because we've done that. All right, I give you 1.4 meters. I give you 1.4 meters. That's a distance, and I also ask for what was the force. If I give you force and distance, and this is in the context of a collision, right? What might we be doing? Work equals force times distance, but it's FD cosine theta. Okay. All right, but our truck was exerting a force in that direction, and this car, the sedan, moves in that direction. Well, what's the angle? What's the angle between those two vectors? It's perfectly parallel, so that means cosine theta goes away to 1. All right, theta is 0 degrees, cosine of 0 is 1. So this means that we get our work is equal to F times D. But we don't know anything about work except for work is equal to the change in energy. So this will be energy final minus energy initial, right? That's our change in energy. So we have the force exerted times the distance it was exerted over is equal to, all right, this is, everything's in the same horizontal plane. So there's no potential energy of gravity. There's no potential energy of a spring or elastic stuff. So it's just KE. It's just kinetic energies, KE final minus KE initial. Well, we get force times our distance, 1.4 meters, is equal to kinetic energy final, 1/2 m. This was of the sedan, 1650. Final, 62.4. Yeah, we'll just do 2 sig figs. No, we'll keep the full number. 62.43 squared minus 1/2 m v squared, but this one's v initial, which was negative 25.5 meters per second squared. Okay. Let's see what happens when we plug this all into the calculator. So we get, I'm just going to start on this right side over here because the left side is just 1.4 times our force. We get 1/2 times m times v final squared, 62.43 squared, minus 1/2 times mass, 1650, times v squared. Well, that's negative 25.5 squared. Note, I didn't really need to type that negative sign, did I? Because the squared is just going to take away the negative. But that means on the right side, I get 2,600,000 and around 79,000. So 2,679,000. Just making sure I counted those correctly. Yes. And then on the left side, I get 1.4 times the force. Well, this means what was the force exerted on this? Well, divided by 1.4, 1,000 or 1,910 to 3 sig figs. 1,910,000 newtons of force. Holy frickin' heck. That's a lot of force. That is a lot of force. Okay. Again, that's not a real number. But the question is, how far off the truth is it? How far off the truth are we with that number? Well, let's find out. Let's find out. Okay, so I'm just going to slide this up so we have a little bit more room for part C. All right. So part C. Part C, last part. Let's say that this loud crash dissipated 1 million joules. Oh, that's a lot of numbers. A lot of zeros after that. This loud crash dissipated 1 million joules of energy as sound or thermal or something else, right? There's a lot of different energy A lot of different types of energy. So let's say our crash dissipated 1,000,000 joules of energy. What would the sedan's speed be then? Okay, what would the sedan's speed be at that point? Well, what's really nifty for you on this collision spreadsheet that I have, I show you exactly how much energy there is. All right, that's our initial kinetic energy of object 1, our initial kinetic energy of object 2. And then over here, I have our final kinetic energy of object 1, final kinetic energy of object 2. Well, these numbers, right, final kinetic energy of object 2, this gives us the final kinetic energy of the sedan in joules, right? Because we had object 2 was the sedan. That's how I know we're using object 2's, because object 2 is the sedan's number. So if we take the final kinetic energy of object 2, but now let's say that just decreases by 1,000,000 joules. By 1,000,000 joules. So we have 3,215,000, right around, joules. 3,215,000 joules. So KE final, that's for the sedan, 3,215,000 joules. Okay, but let's say we dissipated 1,000,000 of those joules. Oh, so we're cutting this in close to 2/3. We're basically taking a third of this off. So instead of that number, we would have the kinetic energy final of the sedan. This is a much more realistic number, is only 2,215,000 joules. Only, right? 2,000,000 joules. What would the sedan's speed be then? Okay, well, right, that's 1/2 mv squared. We know that 1/2 mass, 1650, times v squared. Okay, so 2,215,000 joules. Okay, I'll bring this over here. The calculator shrunk on me. There we go. So 2,215,000 joules, then times 2 divided by 1650. All right, this gets me v squared. So I get v squared 2685. 2685 is equal to v squared. How do you get rid of a squared? You square root. So our final velocity of the sedan, in this case, all right, square root, we could just type to the 0.5. It's much faster. 51.8. 51.8 meters per second. That's much better than the 62 we had before. So now instead of going from 25.5 to the left to 62.4 to the right, now we're only going from 25.5 to the left to 51.8 to the right. By the way, that's about 110 miles per hour. And this is a much more realistic number. You're losing about a third of the sedan's energy simply in sound or in heat. A third of the energy, and you're still very much dead. And this is why I'm scared poopless by semi-trucks. I hope you are too. If you walk away with something from this class, physics related, I hope it's drive safe, especially around those semis. Well, if you have any questions, definitely let me know. Otherwise, I will see you next time in class. Feel free to shoot me an email with any questions you got, but have a great rest of your day.